This lecture is about static logic hazards. So to understand this concept, we first need to start by revisiting a very simplistic timing diagram. So recall the gate of an inverter. The symbol is this. It has an input, and its output is just its inverted input. So if you look at the timing diagram for the inverter, here's the input A, and the output A naught is just the inversion of the input. Now we've been used to drawing our timing diagrams as an ideal case. And in the ideal case, what happens is when the change goes from low to high in the input, the change goes from high to low in the output at the same time. But this doesn't actually happen in the real world. When you make a change on the input, it takes time to process it through the gate to give you a change on the output. So in reality, what's happening is something that looks like this. Here's your input, and your change in the output happens some delay after the change in the input. We could even model this in an even more real sense. Let me pull up this diagram that I found online. Nope, I had it open somewhere. There it is. Alright, so if you look at this diagram, again this is showing an inverter. It's showing here that the inverter is low and it switches to high, and then it goes low again. So this is our digital signal that just shows low and high. But what happens in the real world with the circuitry, when this signal goes from low to high for the inverter, the output is going to go from high to low. But as you can see, it takes some time to discharge to get low. So the time it takes to go from high to low is called tau PHL, which means propagation delay. Tau stands for delay. HL means high to low. It's going from high to low. And you see this time is from the point where it takes the output signal to go from high to 50% of the voltage, because once it's below 50%, it's considered a low signal. So as you can see, we've got this propagation delay called TPHL. Then, when we go from low back up to high, you can see that we also have a delay to go TPLH, which goes from low to high. Again, that time is from when we start out low and get to 50% of the voltage. TPHL and TPLH can be different values. As you can see in this drawing, TPHL is longer than TPLH. It could be the other way around. They could be the same, but there's always these two different values. Okay, so why is it important to know this? Well, because this is how real circuits work. There are these delays in the real circuits which can cause static logic hazards. So let me throw out some more definitions for you. What is a hazard? A hazard is an indication that a glitch may be present. Indication that a glitch may be present. And what is a glitch? A glitch is a momentary, unwanted condition in a circuit output. So hazards in circuits are caused by these timing delays, and they can cause glitches, which give you a momentary unwanted condition in a circuit output. And you'll see what all this means in a moment. Let me just further define hazards as they're categorized into different groups. So we have different kinds of hazards. So the different kinds of hazards we have things called logic hazards, and these are due to single bit changes. So if a single bit on an input changes and it causes a hazard, that's called a logic hazard. We also have things called function hazards, which are caused from multiple bit changes. These types of hazards are also classified as static hazards and dynamic hazards. So in a static hazard, it happens when you expect a signal to remain constant, but it does not. And a dynamic hazard, as you might guess, is when you expect a signal to change and it does not. Now we are going to be talking about static logic hazards because they are really easy for us to spot and handle. If you look at the logic hazard definition, you notice it is about single bit changes. And if you recall in our K-maps are set up to have single bit changes between the cells in the K-map. So we can use the K-maps to spot these logic hazards. And they're going to be static hazards because we're expecting a signal to remain a certain value, but it changes and causes an unexpected glitch in the circuit. Okay, so let's talk about how we identify these through an example.